Next part of our chapter 6 is exponential functions and logarithms. So the functions in the form of a to the power of x are called exponential functions. They are defined for all real numbers, and so it means that our domain lies in all real numbers. And the number a is called a base, as you remember. We will have a look closely to the specific function, which is called the natural exponential function. And the exponential function with the base e is called the natural exponential function. We can write it like this or like this. E here is Euler's number. It's irrational number, just like a pi. And the natural exponential function is one of the most important functions in mathematics and natural sciences. So growth and decay in nature can be represented via the natural exponential function. The function has the special property that is derived in the function itself that you can more in details learn in more advanced mathematics course. And here we will just have an idea what is an exponential function. So just remember that the e here is this irrational number. Every exponential function can be represented by the natural exponential function, where the a can be replaced with e to the power of b. So this is true for all a larger than 1 and b larger than 0. In a special case, if a is between 0 and 1, b should be negative. For this reason, whenever we refer to the exponential function, we almost always mean the natural exponential function, because every exponential function can be also replaced by the natural exponential function. So this is how exponential function looks. As you can see here, natural exponential function with any coefficient in the power always intersects y-axis in a point of 1. So the graph of natural exponential function looks like this based on the coefficients in front of the x. As the coefficients goes towards 0, it a little bit expands, and if it's increasing, it moves slowly towards y-axis. And as you may see here, negative coefficient in front, it will just mirror it. The concept that is very close to exponential function are the logarithms. Before looking at logarithm function, let's revise two very important type of logarithms that you will come up often during your future studies. First is a natural logarithm. A natural logarithm also connected to the Euler's number. So if we take, for example, Euler's number and put it to the power of s, this will give us some kind of number of u. So what is a natural logarithm? Natural logarithm is the unique number s that satisfies this equation. So we express our exponent by writing it as the logarithm. It means that this is a power to which we put Euler's number, and then we get u. Because normally logarithm we write it like log, and then we have a base. Log base for natural logarithm will be e. That's why we just write it as ln and refer it as a natural logarithm. And since logarithm represents here the power that we put the Euler's number, we can also imagine it here instead of s. I hope it's clear here. And next logarithm is called decimal, or also log base 10. For the log base 10, we have number 10 to the power of s, and it equals to special number u. And then logarithm equals to s. So our logarithm is this power here for special base 10. And logarithm with the base 10, we just rewrite it as lg. And it means that it has a base 10 here. So it's log base 10. So let's have a look at several examples. Example for the natural logarithm would be e to the power of minus 1. And e to the power of minus 1 will be 1 divided by e. We can rewrite it as a natural logarithm of 1 divided by e, and it will equal to minus 1. So our logarithm here is this minus 1. So these two expressions are equivalent. And for the log 10, for example, we have 10 to the power of 4, which is equal to 10,000. So we can rewrite it as decimal logarithm of 10,000, which is equal to 4. So these two are also equivalent expressions. What is important that the both logarithms have the same zero root, x equal to 1, since Euler's number to the power of 0 and 10 to the power of 0 are equal to 1. If we look graphically, so you can see both have the same root, which is equal to 1. This is log base 10 and this is natural logarithm function. This is how they look graphically. So the natural logarithm function is inverse function of the exponential function. So if you remember exponential function that we saw before, so exponential function looked something like this. And so this will be 10 to the power of x, and this will be e to the power of x. These functions are inverse functions of each other. Additionally, let's revise some logarithmic rules. When dealing with logarithm, there are a number of rules that you have to remember. They are common for logarithms with other bases as well. The first rule here and here, you can see multiplication here. We can rewrite it as a sum, or vice versa. When we have sum of two logarithms, we will multiply u to v. And same with the division. If we have a fraction here, then we subtract logarithm u from logarithm v. And same applies here. It all goes to the power rules. So, and then same goes here. We have 1 divided to v. It means that it's minus natural logarithm of v. Very often we use this rule where we put t outside and just multiply it to the logarithm. The rules of calculating with logarithms and powers help us to transform, simplify, and solve exponential and logarithmic equations. Although today's topic is just functions, we will have a look at exponential and logarithmic equations. Here, this rule is also important. If we have a root here, we can put n in front of logarithm as a fraction. Also, we can change the base of the logarithm. For example, if we want to change our base from natural logarithm to the log base 10, we have to take log base 10 u and divide it to the log base 10 of Euler's number. And vice versa, if we want to change our base from log base 10 to the natural logarithm, we have to take natural logarithm of u and divide it to natural logarithm of 10. So idea here is this: in the new base, u goes here divided by the old base. So basically, using this rule, we can rewrite any logarithm with any new base. And specifically for the natural logarithm of 10, we can rewrite it as 1 divided to log base 10 of e. So next we will solve several examples of exponential and logarithmic equations. So the first of all, here are the few basic transformations. For example, if we have something with the same base, then it means that x1 is equal to x2. Same here. Also, same with the log base 10. To solve exponential equations, we use logarithmic transformations. So, for example, if we have a to the power of x equals to u, we can take logarithm of both sides, and it will equal to natural logarithm a to the power of x equals to natural logarithm of u. If you remember the rule we saw before, we can put this one here and it will give us x logarithm a equal to natural logarithm u, and we will find x as natural logarithm u divided to natural logarithm of a. This is also looks like the formula for the changing bases if you look closely here. If we want to solve logarithmic equation, we use exponential transformation, so we transform it back. For example, if we have natural logarithm of x equals to u, so we can put both of them, as you can see here, to certain exponent, and let's do it by e to the power of, we put here, and this one e to the power of u. If you remember the definition of natural logarithm, so I will just remind you. Natural logarithm of u is equals to some kind of number s, and this s is some kind of a power. And since s here is equal to our logarithm, we can rewrite it as e logarithm of u is equal to u. So this expression will be just equal to u. And if you can see here, this is very close to this expression here. And it means that this expression here is just x. And in this case, x will be equal to e to the power of u. That's it. We can also have a look of specific examples, and every time I will refer to some certain rule, I will just write it in the corner for better orientation. So for example, we have here this equation, and how we're going to solve it. Same as we did before, we will take natural logarithm of both sides. So we'll take natural logarithm of this plus 3 equals to natural logarithm of 4. And again, I will write here down in the corner, if you remember the definition of logarithm. So it means that this expression here will equal to 2x plus 3, right? Will equal to natural logarithm of 4. And after that, we can just solve it as a normal equation. So we will have 2x here and subtract 3 from both sides, which give us this expression. And then we can also simplify it by dividing it by 2. This is how we solved this equation here. So if we have a look at the next equation with a natural logarithm, as I told you before, when we're dealing with natural logarithms, what we do, we use natural exponents. So we will put them to the e. Here we will put our logarithm to the power, and 0 will also go to the power, and e ln to the power of u will equal to the u. It's by definition of the logarithm. It means that this expression is equal to this one here. It will mean that 1 divided to 2 plus x equal to 1. And then we have very simple equation where 2 plus x is equal to 1 and x is equal to minus 1. Let's have a look at the third type of equation with log base 10. First of all, if we have something to the power, then we can put it outside of the logarithm here, like this. And if we look here closely, we can put this 2 back here as well by using this rule. So first expression, we leave it like that. We don't do anything with this logarithm. And here we put 2 back here, which will give us x squared to the power of 2 equals to 21, which will give us log base 10 x to the power of 4 equals to 21. And if you remember, if we add 2 logarithms, we'll have to multiply u to v. So here we'll do the same. We can multiply x to the power of 3 to the x to the power of 4, which is equals to 21. And if you remember by the power rules, when we have multiplication, we add them. So here we will have x to the power of 7, which is equals to 21. Since base of this logarithm is 10, we can put to the exponent of 10. So it will look like following: 10, and the logarithm will go to the exponent. And here as well, we will put 10 to the power of 21. And from here, by definition, it means it just equals to x to the power of 7. So we will have the following: x to the power of 7 equals to 10 to the power of 21. And from here, if we take 7's root of x to the power of 7, we can also take 7's root from 10 to the power of 21. So we will end up having x equaling to 10 with this fraction in the power, which is equal to 3. So that's how we found x. This was just an overview of exponential equations and logarithmic equations and how we can solve them or simplify them.